All right, this lesson is an introduction to chemical equilibrium and Le Chatelier's principle. I apologize in advance if you can hear my dogs barking, because they probably will start barking during this lesson. Okay, so first of all, when we're talking about chemical reactions, we say that a reaction is at chemical equilibrium when both the reactants and products are present in a concentration with no tendency to change. So that means that we're not going to keep making more products or reversing the reaction and making more reactants. So a lot of times students have a misconception that a chemical reaction is something that cannot be changed back to the original ingredients or reactants. That's actually false. So we do have a lot of reactions that can go in both directions, so they can be reversed. So another way that we discuss equilibrium reactions is to say that the forward reaction proceeds at the same rate as the reverse reaction. So if we look at this reaction between nitrogen and hydrogen to make ammonia, over time, we're going to stop making more ammonia. Okay, and this is actually an equilibrium reaction. It is reversible, so we can go from ammonia back into nitrogen and hydrogen. Okay, so in an equilibrium reaction between these, we would have nitrogen, hydrogen, and ammonia present. Okay, so Le Chatelier's principle is going to discuss what happens when equilibrium is disturbed. So when equilibrium is disturbed, the system adjusts in a way to reduce the change. So basically, a chemical reaction at equilibrium wants to stay at equilibrium. Okay, so we call this a stress when we cause a change in the equilibrium. Okay, so we have three types of stress that we're going to look at. So changes in the concentration of reactants and products, so adding more reactants or adding more products is going to stress the system. If we change the pressure, which you should know from gas laws that also could be a change in volume, they're inversely proportional. I'm actually just going to go ahead and add that in here, right? As well as changes in temperature. So we recently covered thermodynamics, so we know that we have an energy exchange in chemical reactions. So depending on whether the reaction is endothermic or exothermic, it's going to cause a different change to the equilibrium. Okay, so when a stress is first applied to a system, equilibrium is disturbed and the rates of the forward and backwards reactions are no longer equal. All right, so changes in concentration. I think that it is a little bit easier to kind of think about the logistics of this situation rather than trying to memorize the information on this slide, but I'll go through it anyways. So if more of a substance is added to a reaction at equilibrium, the system will shift to remove the excess amount of that substance. Okay, so if we're adding more reactants, we're going to get rid of that by making more products. Or if we add more products, we can get rid of the extra products by shifting and making more reactants. If a substance is taken out of a reaction at equilibrium, the system will shift to produce more of the substance that was removed. So we'll go through a little bit more of that on the next slide. All right, and then it's really important that you know that there's only certain states of matter that affect equilibrium. So aqueous and gaseous atoms or molecules are going to affect equilibrium, but solids and pure liquids do not affect equilibrium. So make sure that when you look at the chemical reaction, remember that the states of matter are going to be in little subscripts. So aqueous is going to be AQ in parentheses. Gas is going to be G, solid is S, and liquid is L. We're not going to get into why those don't affect equilibrium in this course. It's a little bit beyond the scope of this class. Okay, so here is an equilibrium reaction. So let's pretend we have a lid here on this beaker because these are all gases, so of course they would escape in this scenario. But we have nitrogen gas reacting with oxygen gas to form nitrous oxide. Okay, and it also the reaction can reverse. Okay, so we can get rid of this and make more oxygen and nitrogen. Now, the way I'm going to have you guys solve the equilibrium problems, we're going to be thinking about this reaction as kind of like a teeter-totter. But I think it's really important to note that that's just a representation. It's just a trick to solve these problems. A chemical reaction is not really like a teeter-totter at all. So if you look here, if we've got this equilibrium reaction, notice that we have nitrogen, oxygen, and nitrous oxide all mixed up in this beaker. Okay, and that's always going to be the case for these reactions. We don't have all the reactants hanging out on one side and all the products hanging out on the other. Which is going to become a misconception as I show you how to solve these problems. So just keep this in mind that all the reactants and products are mixed up all together. But what's important for an equilibrium reaction is that you see that there's reactants and products present. Okay, a reaction that is not an equilibrium reaction, all of the reactants, if they're present in the correct amounts, will all form products. And then the beaker would just be full of products. Okay, so as I just mentioned, we kind of think of these as like a teeter-totter. So we've got the same reaction as the last slide. We have nitrogen reacting with oxygen to form nitrous oxide, and notice that we use this double arrow, and that means that it is an equilibrium reaction. The reaction can proceed in both directions. So if the reaction's at equilibrium, you can think about it as everybody's happy, everything's equal. Okay, that is not necessarily what an equilibrium reaction means. It doesn't mean they're present in equal amounts. They're just present in an amount that doesn't want to change. But just for the purposes of solving whether or not the reaction shifts to the right or the left, I want you guys to just think about it as being equal. Okay, so everything's happy, it's in line. We've got the same amount of nitrogen and oxygen on both sides. So 2 little blue balls, 2 little yellow balls. Okay, 2 and 2. So now we're going to disrupt equilibrium. And we're saying that we're going to increase the concentration of nitrous oxide. Okay, we're adding more NO, right? If you add more NO, that's going to make it heavier on this side. Okay, now in order to make it evened out again, the reaction is going to have to shift to the left. So what that means is we're going to try to get rid of this extra NO by making more reactants. Okay, so the reaction shifts to the left, which means we're going to make more reactants. Okay, so at that time, the concentration, if we're going to get rid of some of this, the concentration of nitrous oxide is going to go down, the concentration of oxygen will go up, and the concentration of nitrogen will go up. Okay, so that's what it means if we're shifting to the left. So I'm going to first ask you, okay, which direction does the reaction shift if I add more NO? Okay, so that's going to make it unbalanced on this side. It makes this side heavier. So it's going to shift to the left. Okay. And if we shift to the left, that means we're making more of the stuff on the left and we're losing stuff on the right. All right, so this one, now we're saying we're going to remove some oxygen. Okay, the concentration of oxygen decreases. So if we remove oxygen, then it's going to become lighter on that side of the teeter-totter. So in order to counteract that, we need to shift the reaction again to the left. Okay, so we need to make more of this stuff to make it heavier on that side. Okay, and remember, it's not literally making things heavier or lighter on one side of a reaction. All of these are mixed up in the beaker. This is just a representation. Okay, so whichever side is too light, we need to shift in that direction to make more of it. Okay, so if we are making more reactants, then that means the concentration of nitrogen and oxygen are going to increase, and nitrous oxide is going to decrease. All right, if we increase the concentration of nitrogen, okay, so we're adding more to this side over here, to the reactant. So in theory, it's like it gets heavier on this side. We're going to need to shift to the right to make this balanced. So we'll make more products so that this reaction will go back to equilibrium. Okay, I'm going to show you guys with my document camera. This is going to be a little bit strange, but we're going to try to make it work. All right, we're going to use this reaction again. Okay, so I recommend using a pen or a ruler for this. So let's say this is going to be my little teeter-totter. Okay, and we're looking at that reaction of nitrogen plus oxygen to go form nitrous oxide. So if I add more nitrogen, okay, notice nitrogen is in the reactants, it's on the left-hand side. So if I add more, if I think about it as a teeter-totter, okay, it got heavier on that side. So which direction does it need to shift to get back to equilibrium? So I would need to shift to the right to make it back to equilibrium. Okay, so if it got heavier on this side, I need to make more products. I need to shift to the right for it to become balanced again. If I were to add more nitrous oxide, more NO, okay, that's on the right-hand side of the reaction. It's a product, okay? So I would need to shift to the left to become balanced again. If I remove NO, which is on the right-hand side, it's going to get lighter on that side. I would need to shift to the right to make that balanced again. Okay, so you're looking at which side you need to make more of in order to make it back at equilibrium, to make it balanced. If we remove oxygen, so see that oxygen is in the reactants, it's on the left-hand side. So if I remove it, it's going to get lighter over there. So I would need to shift to the left for that to go back to equilibrium. Okay, and then I have the beaker there still so that you guys can see. We are not really working with the teeter-totter. They're all mixed up in there. Okay. Okay, so we will be doing a lab where you guys can actually see equilibrium shift. And those of you guys who saw my gender reveal, I was doing an equilibrium reaction. I was using the Chatelier principle to shift between pink and blue. Okay, so in this reaction, instead of pink and blue, we have a light blue solution, and we have a darker, like a purple blue solution. I think I've got a picture of them right here. Yep. So when the reaction is favoring this side, so if we have shifted to the left, then we'll see that the solution will be pale blue, like this. And if we shift the reaction to the right, it's going to be a blue purple. Okay, so that's in the products. So here, actually, let's go back to the document camera and do some practice. So looking at this reaction, if we add more water, which is right here, what is going to happen? Well, you might want to say, oh, well, it's going to get heavier on this side, but there's one thing you probably missed, and that's that this is a liquid. So I said on a previous slide that liquids don't affect equilibrium, so that actually is going to do nothing. Trick question. How about if we add more of this compound, okay, this copper ammonia compound. So if I add more of that, that's a product. So I'm adding more to the right-hand side. I'm thinking about it that way. I would need to shift the reaction to the left to get that balanced again. Okay, so if it gets too heavy on one side, we're basically going to make more of the other side to balance it out. If we remove ammonia, which is this NH3 right here, it's aqueous, so it will affect equilibrium. If I remove that, it's going to get lighter on the reactant side. So I will need to shift to the left to get that back to equilibrium. Okay, and we would actually see the color changes there if we did this reaction. So you'll do that with the pink and blue one like I used in my gender reveal. Okay. So actually, we'll move to the next slide. Okay, so you should practice these as we go along using a pen or a ruler. Okay, so if we were to remove COCl2, okay, so you can think about it as this side becoming lighter, what is going to happen to equilibrium? So try that really quickly. Okay, and yes, it would shift to the right. So if it gets lighter on this side, it would need to shift to the right to get back to equilibrium. Add chlorine gas. Okay, so you should have done it so that the left-hand side got heavier. Okay, and I'm going to put that in air quotations, heavier. Didn't really get heavier. Just added more of it. So it's going to counteract that change by shifting to the right. It's going to get rid of some of this extra chlorine by making some more of these products. All right. So for this reaction, if you remove oxygen, okay, so here's oxygen. It's on the reactant side. Give you a second to work through that. So if you removed oxygen, it should have been getting lighter on the left-hand side because it's a reactant, and that would cause equilibrium to shift to the left. If you add PBS, lead 2 sulfide. Okay, now you probably want to say that it will shift to the right, but some of you guys hopefully caught that lead 2 sulfide is a solid, so there would be no change to equilibrium. Okay, if you add sulfur dioxide, okay, it's a gas, so it will affect equilibrium. Okay, so you should have had your little teeter-totter get heavier on the right-hand side, okay, because it's a product, and that would cause equilibrium to shift to the left to counteract that change. So we're going to get rid of some of this extra sulfur dioxide by making more of the reactants. Okay, so I got another reaction here. Okay, if you add sulfur, and hopefully now we caught, yep, that's would be no change because it's a solid. Solids don't affect equilibrium. Okay, remove water vapor. Okay, we say water vapor because this water is a gas. So you should have done that as the right-hand side getting lighter because we removed water. So we would need to shift to the right to get back to equilibrium. All right, and if we removed hydrogen sulfide, you should have the left-hand side, the reactant side, getting lighter, so to speak. So we would need to shift to the left. Sorry, I meant to say left-hand side, the left-hand side getting lighter. I apologize. Okay. And we'll cover pressure and volume changes on the next presentation.